Ew, the Virgo cluster. That's like something I should know about.
Good, because I will be talking about it. One second.
Maybe we can get into the appendix.
Yeah,
Use this one too.
okay. Yeah, it was, of course, just working. Let's wait 1 minute. I'm just gonna do the whole,
Turn it on.
yeah.
Plug it in just in case.
Pardon? Yes, please.
Nice to see you both. I'll tell you that.
Okay.
Just click into. Yep. Yeah.
Okay, you wanna try it? Good.
Yeah.
All right. Here we go. Thank you, Hugo. Okay, perfect. Pardon?
How was your last day of science?
I was rehearsing by myself, and it was the worst, definitely. Kept on restarting.
Yeah.
Thank you for coming and being so proud of us.
So welcome to
Welcome to the PhD defense of Christine Corbett Moran. Christine got a degree from MIT in 2007. She was both a major in computer science and physics, with minors in both math and philosophy. So we should suspect that she had diverse interests. She first came here doing a master's degree, which was on massive visualization of astrophysical data sets. During the time that she's been a PhD, she also did some teaching in Manila and Jerusalem. That her vita actually lists 12 hobbies, but I know that there are a couple that aren't there. she's known for was starring with the roller derby girls.
Two of them are here.
Good. So they'll be able to do some checking on the question period. So her thesis title is Galaxy Clusters as Cosmological Probes, or maybe that changed to this title, but it's one of those.
Thank you, George, for the nice introduction.
That was the title of the talk, but the actual formal title of the thesis is a bit more boring. So thank you for the great introduction. Today I'm going to talk to you about my thesis, Cosmological N-body Simulations as Probes of Gravity, and 3 projects I did during the course of this work: structure finding in cosmological simulations, globular cluster formation in the Virgo cluster, and chameleon F(r) gravity on the Virgo cluster scale. But before we get to that, I'll start with an introduction to cosmology, and specifically our concordance cosmological framework. Cosmology is the science or theory of the universe as an ordered whole and the general laws which govern it. And our concordance cosmology incorporates general relativity, the Big Bang and expansion, inflation, cold dark matter, and a cosmological constant. Here is a brief timeline of the universe. I'll go over each of these in more detail, but we have the Big Bang, inflation, growing quantum fluctuations to cosmic scale. About 300 years after the Big Bang, the baby photo of the universe, the cosmic microwave background radiation, which we use as initial conditions for our simulations. It gives us a picture of the early universe. And then we have the first stars, the expansion of the universe, and now, the present day, we observe the accelerated expansion of the universe. Some of my work takes these initial conditions in simulation to explore globular cluster formation site, modify gravity signatures, finding structures or halos in these simulations, and comparing to observations in near present day galaxy clusters. So let's start out where the universe started, which is the Big Bang. Hubble observed in 1929 that galaxies farther from us were receding faster. And from this, taking this back in time, we have everything being closer together, culminating with the beginning of the universe, the Big Bang. This wasn't the only evidence for the Big Bang. There's also this cosmic microwave background radiation that I mentioned before. This was observed in the 60s first, but we now have more and more precise observations that show us that the universe at this time was roughly homogeneous and isotropic, the same in every direction. And if we zoom in a little bit here, we see that we have some large-scale correlations between different points on the cosmic microwave background radiation, as well as small fluctuations. It's not completely uniform. And these puzzles, why this might be the case, was helped resolved by the theory of inflation, developed by Alan Guth in 1980. And inflation explains those large-scale correlations by, in the quantum fluctuation shortly after the Big Bang, inflation grows those to a cosmic scale. And the differences in the cosmic microwave background come from those early quantum fluctuations. And it is exactly those that evolve later into the structure we observed in our universe, such as galaxies and galaxy clusters. Understanding this phenomenon was enabled by our theory of gravity, general relativity. And I can't give a full introduction to general relativity here. That would take an entire semester or graduate career. But here's some intuition that space-time tells matter how to move, and matter tells space-time how to curve. General relativity was developed by Einstein in the 1910s. And here are some complicated equations. But if we go back to this mnemonic, if you will, we have on the left-hand side of the Einstein field equations, as they are so called, we have space-time telling matter how to move. And on the right-hand side, we have matter telling space-time how to curve. And I'll come back to this because I will be dealing with cold dark matter, that is additions to the right-hand side, as well as modifications of gravity, that is changes to the left-hand side. General relativity also predicts very precisely a phenomenon called gravitational lensing. That is space-time telling matter how to move. So space-time can actually bend light, and we can observe this very precisely. It's a phenomenon called lensing, and from this bending, calculate exactly the matter distribution or the mass intervening. So now we have the Big Bang, we have inflation, and there are two remaining ingredients we need to understand before embarking on research in cosmology. And the first is cold dark matter. The need for cold dark matter was first recognized by Fritz Zwicky, of Swiss origin, working at Caltech in the US in 1937, and he observed on the outskirts of a galaxy cluster called Coma much higher velocities than he might have expected based on the luminous material alone. And this led him to hypothesize that there was some dark material, dark matter, that interacted only gravitationally. Likewise, this phenomenon was observed on the galaxy scale by, for example, Rubin and Ford in 1970, who observed on the outskirts of Andromeda the same phenomenon, and I'll go over a plot about that shortly. This was also confirmed by some of the first numerical simulations and body simulations that explored different scenarios and showed that those scenarios without dark matter produced unstable galaxies. So here's an example plot. We have velocity on the y-axis, and on the x-axis we have radius. And we see that the velocity curve is very flat, and that is what we might expect if we had dark matter. Without dark matter, we would get a dropping velocity curve. This wasn't the only evidence for dark matter. Large-scale structure observations from, for example, galaxy surveys, such as the SDSS, the Sloan Digital Sky Survey, showed a filamentary structure with filaments and voids, and this is exactly what is produced by n-body simulations incorporating cold dark matter. and not something we might expect without it. We also have more evidence from objects that lens light, and as I went over before, we can use this lensing to map matter and compare that map to that you might obtain from the luminous distribution and infer the mass and show that there is a large dark component. The smoking gun evidence has occurred. Smoking. You're not supposed to smoke in the lecture hall, but there we go. In the last 10 years, collisions of galaxy clusters have been observed, and one can compare the X-rays emitted from gas and the gravitational map produced via lensing, and show that the two distributions differ. So now that we have cold dark matter, we need one final component to embark on research, and that is some explanation for the late time accelerated expansion of the universe, which was first observed in the early 90s, and in the late 90s, two groups observed very precisely with supernova, type 1a supernova, which have a very regular explosion, allowing you to infer distances very precisely, inferred that the universe was not only expanding, as was observed by Hubble, but was accelerating in its expansion. And this jived well with observations from the cosmic microwave background that the geometry of the universe was flat, and the density required for that was greater than the matter density alone, and that missing component could be the cosmological constant. So before going back to the equations of general relativity, on the left-hand side we had the geometrical terms, and one of those terms could potentially be a constant, and that constant was first introduced by Einstein himself to explain his desire to have a static universe, a universe that doesn't expand, doesn't change. This was quickly done away with when it was realized by Hubble and by others that the universe was in fact expanding. There was no need for a static universe. But it was realized later, when it was observed that the universe was accelerating in its expansion, that this cosmological constant could be easily reintroduced without changing fundamentally the theory, and neatly explain this accelerated expansion. So I've given you a picture of our concordance cosmology, the Big Bang, inflation, cold dark matter driving structure formation, and the cosmological constant explaining the late time accelerated expansion of the universe. Cold dark matter and the cosmological constant have matured as leading explanations for these variety of phenomenon that I have presented, but there are other explanations, and I'll briefly go over a couple here, only one portion of which my research touches upon, but I find interesting nonetheless. And those are alternatives to cold dark matter and alternatives to the cosmological constant, and why one might, as a researcher, explore these. So for cold dark matter alternatives, I have 4 problems coming from n-body simulations that I colorfully refer to as the 4 horsemen of the cold dark matter apocalypse. And those are the missing satellites problem, the cusp core problem, the too big to fail problem, and the angular momentum bailout problem, which I also named because it was related to too big to fail. If it's too big to fail, you have to bail it out. So with angular momentum bailout, this was that galaxies were losing too much angular momentum in simulations as compared to observations. This was later shown not actually to be too much of a problem if you incorporated additional physics to cold dark matter, such as baryonic physics, the matter that you and I are composed of, and increase the resolution of the simulations. This problem went away. This goes to show you that these 4 horsemen aren't necessarily horsemen of the apocalypse. Perhaps that just means that we need to do more precise simulations at higher resolution with more physics. I'll also go over one more problem in detail, and that is the missing satellites problem. So satellites are gravitationally bound structures that orbit, for example, a galaxy, so smaller dwarf galaxies or even globular clusters, which I'll go over later. And n-body simulations predict many more of such satellites than are actually observed, and this is called the missing satellites problem. So due to these problems, there have been two alternatives to cold dark matter that have been presented. One predated these problems, but one additional problem may be, cold dark matter, it isn't yet observed by particle theorists or predicted by the standard model of particle theory. So one might say, well, why not modify the theory of gravity itself? And in fact, some physicists tried to modify Newtonian dynamics, and later this was reformulated such that it was a relativistic theory itself. This, however, was quickly shown, although it could explain some of the rotation curves that were observed, not to adequately explain the other important evidence, such as gravitational lensing and the smoking gun evidence of the bullet cluster. So this was quickly disfavored. There is ongoing research that perhaps the dark matter particle isn't cold, and the temperature of the dark matter particle refers to its temperature or velocity at the time of decoupling from baryonic matter, from normal matter. And if we modify that, we get different structure formation properties, which we can explore in simulation. And we see on the right-hand side with hot dark matter, we don't get as much of that filamentary structure. Structure formation is smoothed out. So that's very strongly disfavored. But warm dark matter can potentially cause fewer satellites to form, for example. So could potentially be some solution to part of these problems. But it remains to be seen. And to date, the favored model, and the model that I work with in all of my simulations, is cold dark matter. So next, which relates more to my research, is cosmological constant alternatives. So the cosmological constant has two big problems, which I call colorfully the two dragons of the cosmological constant. And the first is the eponymous cosmological constant problem. And that is namely that particle physics, unlike dark matter, the standard model of particle physics, does predict a cosmological constant. However, the value that it predicts and the value that is required from our cosmological observations is over 100 orders of magnitude different. So while physicists find the cosmological constant, cosmologists find it a very neat explanation, this mismatch is an issue. Another issue is the coincidence problem, namely why is the universe accelerating in its expansion exactly at the present epoch, the epoch that you and I live in. And humans, whenever we have traditionally decided we're at the center of the universe, it's all about us, we have been wrong. So it is a philosophical problem, to go back to my philosophy minor, why the accelerated expansion is occurring exactly now. And two alternatives to the cosmological constant are considering modifications to the right-hand side of Einstein's equation, adding, for example, extra scalar field or fields, or modifying general relativity, the initial equations itself. And we all know a great way to get headlines is to prove Einstein wrong. And here's someone proving Einstein wrong by finding a good sandwich, perhaps in Zurich. He did his PhD here. My favorite sandwich place is a falafel place down on Langstrasse, incidentally. So we could actually go ahead and prove Einstein wrong, not necessarily because he himself has modified the field equations in the past by adding this cosmological constant and then later removing it, and now we've added it back again. And there's no a priori reason why one particular set is better than another, other than that we as physicists often like simplicity, and the simplest explanation is often the most favored one. So if we go ahead and make this much more complicated, for example, in an f of r gravity theory, which I will go into in more detail later, we could, for example, potentially reproduce the late time accelerated expansion without resorting to a cosmological constant that is much, much larger than that predicted by particle physics. However, we still have the task of matching observations, and general relativity matches extremely well on the solar system scale and at the cosmic scale in particular realms. So to do this, these alternative models traditionally employ something called the chameleon mechanism. And a chameleon changes its colors depending on its environment. And likewise, a chameleon formulation of one of these alternative models, for example, f of r gravity, will change its behavior, change its modification based on the local environment. So for example, in high density regimes, such as our solar system, reproducing general relativity precisely, whereas on cosmic scales, producing those modifications that result in a late time accelerated expansion without a cosmological constant. So it remains to be seen whether the chameleon can slay the dragons of the cosmological constant, but one portion of my research involves exploring exactly such alternatives in simulation. So here are some methods that I use throughout my research, and I'll give a very short introduction. First are n-body simulations and galaxy clusters, as well as structure finding. Here is a fantastic simulation performed by Jörg Diemen here at the university, and you can see, if I go ahead and play this, oops, let's go back. There we go. We can see that filamentary structure that was observed by SDSS, and we can also see gravitationally bound structures. These are called halos, and they're merging hierarchically to form structure. And these n-body simulations can explore the interaction of cold dark matter particles in simulation and help us make predictions about the observable universe itself. The laboratory that I use are galaxy clusters in simulations, and galaxy clusters are groups of galaxies, and they are the largest gravitationally bound structures in the universe. As such, they comprise sort of an island universe that is very suited to exploring these theories and making observable predictions. So for structure finding, I'm already going to get a little bit into my research and talk about some work that I did about structure finding in cosmological simulations. So halos, as I mentioned, are gravitationally bound objects in simulation, and these host structure in the universe, such as galaxies and globular clusters. So here on the x, y, and z axis, I have spatial coordinates, and this big blue sphere is one halo, and each of these small dots is a subhalo. So those are subhalo satellites within a host halo. And the research questions I chose to address are which halo finding algorithm performs the best. There are many alternatives, and deploying these algorithms is fundamental to understanding and analyzing our n-body simulations. And what are the errors associated with these various algorithms? So I helped to develop a counterpart halo catalog to compare many different halo finding algorithms. So on the y-axis, we have the fraction of objects that a particular halo found out of the total number. And on the x-axis, we have the number of particles in that halo. And a couple things. First, that the numerical technique that I used to compare one object to another object found by another halo finder was the number of shared particles squared over the number in each halo individually. And this was the merit function that was maximized to find the counterpart halo. So that is the same halo found by different finders. And something that you can pick out from this plot is that the low number of particles correspond to low resolution halos, and they're less robust in general. There's a big variation among the performance of these various halo finders. The greater the resolution, the more robust your detection of the halo finder is. And we found that the scatter of various quantities, such as the mass function, here's the number larger than a particular halo mass, and we have on the x-axis the mass, And here we see that the mass function is very similar between finders, which is great because that means that there isn't too much variation between these various algorithms, and we can have some particular confidence in the error bars when deploying them. So we see that the scatter of the mass function is about 10%, and that the scatter of position, velocity, and size of common halos, that is the same halo found by many different finders, is very small, actually. It's on the order of 1 to 3% relative to the total scatter. So our results, I show personally a robust way to construct this counterpart halo catalog that was used throughout our work to show the scatter of these various quantities. We show that for most halo finders, for most halo properties, the agreement is at the 1% level for common halos, and that a collection of particles, the algorithm to collect the particles and the unbinding procedure impact agreement. And this paper is used now as a reference paper to show errors and suitability of various subhalo finders and halo finders. So now I'll get into the core of my research, my 2 core research projects in addition to structure formation research, and that is globular cluster formation in M87. So first I'll start out by telling you what globular clusters are. Globular clusters are spherical balls of stars that have been long observed. Perhaps the most wonderful of all the star clusters are those upon which hundreds and hundreds of thousands of faint stars are all gathered together in the shape of the globe. So these clusters actually comprise tens of thousands to millions of stars with present-day observations, but the qualitative picture is correct, and here's, in fact, a picture of an actual globular cluster, and these clusters orbit galaxies such as ours as satellites. And they have several interesting properties, which lends well to scientific questioning and research that I did. So this is a bit of a complicated plot. We have mass on this y-axis, we have color, and we have metallicity. And using the information from the left plot, we can add that to the right plot in terms of color. And we can see that globular clusters, systems of globular clusters, are divided into 2. We have an older blue metal-poor system and a younger red metal-rich system. And in general, both of these sets of clusters are very old. These clusters formed in the very early universe. So this lends to the scientific question, why are the populations so old? How did these objects form? And what separates these 2 populations? And these are the questions that my research contributes to addressing. So one popular formation mechanism for these clusters was pioneered by Ben Moore, who's here at our institute. And here's some pretty plots from Moore et al. 2006. And we have, if we mark particles or portions of the simulation that are at very unusually high density at high redshift, if we trace that all the way to the present day, we will get a very similar distribution to the present-day globular clusters. So one might hypothesize that the globular clusters formed in exactly such sites as the left, so unusually high-dense regions of the very early universe. And my research showed, in complement to previous research, that this was a very viable candidate formation mechanism in, for example, M87, which is the brightest central galaxy in the Virgo cluster. And here on this plot, I have surface density on the y-axis and radius on the x-axis. And in the blue, I have actually observations of globular clusters in this system. And we can see that these various redshifts, the z's, are various times. And there's one particular time for this particular mass on the order of 10 to the 8 solar masses that matches very well with the present-day globular cluster population. So in this example, globular clusters forming at a redshift of 9 in halos of mass about the 10 to the 8 solar masses would be a very viable model for forming the present-day M87 globular cluster distribution. To do this research, I developed a new split hierarchy technique. So you might have noticed that on the plot before, where we were marking particles at very high redshift, we needed not only the particles at the high redshift, but also we needed present-day properties. And also, the more particles that you have, my halo finding research helped show, and intuitively makes sense, the more robust your detection of such halos are. So you really want to have the highest resolution possible, the highest number of particles in your halos at this very high redshift. However, running those simulations all the way to the present day is computationally infeasible. So because we are interested in these present day structures, I was able to show that one could mark the particles above a particular mass cut in a very high resolution simulation in red, trace that back to the initial conditions of a low resolution simulation, and run the same simulation all the way to the present day. So in essence, grouping the high res particles into lower resolution particles. And with this, we were really able to push the resolution of our simulation to the requisite level to address these issues at the cluster scale. And here I show that this technique is in fact quite functional. So on the y-axis, I have surface density, and on the x-axis, I have radius. And here we have in the dots is the low resolution simulation, so basically the end result that we want to get. And in the red is the high resolution simulation, and we see that they match. The split hierarchy technique matches very well with the full simulation. So we were able to deploy this technique to show exactly the results that I developed before. And we helped to actually show some observable predictions. So here I show the number of cumulative globular clusters on the y-axis, and on the x-axis I have radius. And in the green, I have the intra-cluster globular clusters. That is, globular clusters that aren't actually bound to a particular satellite or galaxy within the cluster itself. And this is an observable prediction that I make about 300 intracluster globular clusters. And whether this is actually observed or not can favor or disfavor my particular formation scenario. So a summary of additional results that I obtained in the course of this research is that our model can consistently form the requisite blue globular clusters by a redshift of 9. Our model relaxes previous assumptions that addressed formation in M87 and Virgo. We predict a rising velocity dispersion profile, and we predict about 300 intracluster metal-polar globular clusters in the Virgo cluster. So now I'll tie in to my final project before going into a summary, and that is modified gravity in simulation. So before I went into various alternatives to the cosmological constant, adding a scalar field, or actually modifying Einstein equations themselves, and I explored one such alternative, f of r gravity, in which the Einstein-Hilbert action becomes a general function of the Ricci scalar. So here we have the modified action, and from that we can derive a perturbation of the scalaron. So in general, these modified, particularly the f of r gravity, is equivalent to a scalar field. So it is a matter of interpretation, whether one interprets it as a modification on the right-hand side, the matter side, or the left-hand side, the geometrical side. Throughout my work, I followed the geometrical interpretation, but one effective way of thinking of things is actually we have a perturbation of a scalar field, which I refer to as a scalaron. So this is coupled to a modified Poisson equation that is also derived from this modified action. And these two coupled equations are those that govern the gravitational behavior and the evolution and structure formation in the universe. So I mentioned before that we need a chameleon model of sorts, a way to match the local observations very effectively of general relativity, and also reproduce the late time acceleration on cosmic scales. And here I deploy a Hughes-Sawicki model. And this model, this C1 and C2 are tuned to match the background evolution of the universe, and this n is a free parameter. And we can consider Here's the chameleon. Some research questions associated with this. First, is the theory observationally viable at all? Second, well, what would be observables to actually distinguish various models, different model parameters from each other and from our concordance cosmology, lambda CDM? So current observational constraints, here on the y-axis, I have the background value of the scalar field at present, and on the x-axis, I have scale. And I consider models in a variety of ranges, some that are already disfavored by observations, and some that still fall within the realm of plausibility. And the reason why I do this is that anything much smaller than this is so close to lambda CDM, it remains very hard to observationally distinguish. Anything much higher is strongly disfavored. So I consider models in this range, and the very strong modifications that are most likely disfavored help us develop intuition for where the modifications might actually come into play in modifying structure formation. So I consider models in this range. And that namely corresponds to a value of 10 to the minus 4, 10 to the minus 5, and 10 to the minus 6. And I refer to this as the strong model, which is more disfavored, medium model, and a weak model. So F4, F5, and F6. And you'll see this a bit in the plots that are upcoming. So weaker than this is very close to lambda CDM, and stronger than this is very strongly ruled out. So what is the actual effect? Well, we can actually consider two extremes. First is an underdense regime, and in this regime, gravity is enhanced by a factor of 1/3. We have an intermediate density regime in which simulations, the equations are highly nonlinear, and simulations will tell what actually the effect, the modification of gravity will be. We can also consider an overdense regime, such as our solar system, and in this regime, general relativity is fully restored. So you can remember these icons, and here when you see this, we have an enhancement of gravity, and here when we see the chameleon, we know general relativity is restored. Some terminology as well from the field is that this is referred to as the unscreened regime, and this is referred to as the screened regime. That is, the fifth force is screened by the chameleon effect. This intermediate regime I refer to personally as the transition regime. So here are some physical values for the very strong model at a redshift of 1.5. We have at all radius, here's the fifth force over standard gravity, and we would expect this to be 1/3 in the modified gravity regime, in the unscreened regime, and 0 in the screened regime. So we see here, plotted versus radius, that at all radii that we consider, the fifth force is very strongly in effect. It's equal to exactly 1/3. So in the weak model at this redshift, we can see actually there's an effect with radius. So here at very high radius, we're in the unscreened regime. At intermediate radius, we're transitioning, and at small radius, we're in the screened regime. And that is because of the effect of the density of the main halo itself. So what are some observable signatures? That was the research question. Here is the surface density plotted versus the radius. And we can see that F6 and lambda CDM, that's the black and the blue, the weak model, and lambda CDM are very, very close. F4 and F5 have a very slight deviation in the center. This is where baryonic effects can come strongly into play. So this observation gives us very little information. However, if we go ahead and look at the velocity dispersion versus radius, we can see, again, that F6 and lambda CDM are very close. But we do see that F5 and F4 both have a higher velocity dispersion here. So that's an observable modification that we can see. We can also see this visually, that structure is forming much more slowly in the modified gravity models in the strong modified regime, whereas F6 and lambda CDM are predictably very close. So one way to compare with observations is for a given satellite, you may want to measure whether it should be screened or unscreened. And if it's screened, you don't expect any modified gravity effects. But if it's unscreened, you might expect modified gravity effects such as enhancement of the velocity dispersion at particular redshifts. So one way to measure this is to compare the lensing mass and the dynamical mass. The lensing mass is probed by that surface density plot that I gave you before. The dynamical mass is probed by the velocity dispersion plot that I gave you before. Lensing is also obviously probed by lensing itself. So we can do this by actually computing the dynamical mass in simulation. And that modified Poisson equation before that I presented, we can recast that in the form of our usual Poisson equation and represent that density difference by an effective rho here, perturbation. So that is the measurement of the dynamical mass in simulation. And here, this value is going to be 0 and screened if it's 0, and unscreened if it's 1/3. Another way to potentially measure this screened or unscreened property in observation is to compare the internal potential of a particular halo and the background value of the scalar field and the external potential of other halos nearby influencing that halo's screening properties itself. So here it will be screened if that internal potential is large compared to the background value of the scalar field, or if the external potential is large compared to that background value. And here, each modification introduces an effective Compton wavelength that is a range of the fifth force modification. And here this equation is simply summing over all the neighbors upon which the fifth force may have some impact and summing the potential impact from that. So I actually compared these two for satellites in simulation. And here on the y-axis, I have that external potential value we found for all the satellites, and we were able to actually perform the first zoom simulation with the eCosmog code that is a modification of the Ramses code developed here at university. And with this zoom simulation, we were able to, for the first time, resolve satellites very well. We found for all these satellites that were resolved, the internal potential was not high enough to screen them. However, the external potential, here we have mass on the x-axis, and this is the measure of screening, the delta M. And when it's about 1/3, we are in the modified gravity regime, and when it's near 0, we are in the screened regime. So here, if I divide these two, above we have blue points, and below we have yellow points. So we have unscreened and screened. So this is one way to use the external potential to predict whether the satellite galaxy is screened or unscreened. Now you may notice that below there is actually a dark blue point in a sea of yellow points. And where does that come from? Well, we can see this from the two-dimensional or even three-dimensional, as I presented in the paper, distribution. So here again we have the measure of screening. So unscreened to screened in the dark blue. And you can see as a function of radius from the main halo that the closer to the main halo center, the more screened, more dark blue. But there are some exceptions. There are dark blue points in the outskirts, and those are particularly those that are close to a big subhalo. Those are also screened, even in the outskirts, due to the external potential of that subhalo. So a summary of the results from this paper are that I found that the velocity dispersion and or the lensing signal profile at particular redshifts for particular models are potential discriminatory mechanisms between different models and lambda CDM. I show a characteristic radius above which the chameleon mechanism fails to work, and I quantify the environmental dependency of the screening effect. I also show that this quantity, the external potential, is a reasonable proxy for the screening level of a satellite. So as a summary, here again we have a universe. I went over the history of cosmology in my research, taking initial conditions of the universe, exploring and simulation, globular cluster formation sites, modified gravity signatures, halo findings, simulation, and observables that we might be able to see and compare in the present-day galaxy clusters.
some perspectives for future research. This globular cluster formation mechanism relies upon globular cluster formation being truncated at very high redshift. One candidate for this truncation is reionization, the effect of reionization. To explore this, full radiative transfer simulations are necessary. Modified gravity I have explored without baryonic effects. Some authors are actually already adding these into simulations, and they've shown large degeneracies. However, verifying and exploring exactly the range of those is an area for future research. In addition, these alternative cosmological models are much more difficult to solve numerically, and that means more research in terms of robustness of halo finding, as well as robustness, convergence, and resolution studies of the codes is necessary. So to conclude, here are the 3 papers I have published during the course of my PhD stay here at the University of Zurich, and I am happy to take questions from the audience at this time. Thank you very much.
A few questions before we go to closed session. Would you like to start?
Okay.
So, in the for the halo finding, what was the smallest halo you can find? And on the
So it depends on the halo finder, first of all. And so some halo finders can't even find subhalos.
That
So
means,
that means,
substructure of a particularly large halo. So it really is very, very dependent on the halo finder, and it also depends on the resolution of your simulation. But in general, we find that 100 or more particles is required for a robust detection of a halo in your particular simulation.
And is that consistent with the halo numbers, like with the missing satellites problem, or is there still some inconsistency?
Well, that number doesn't necessarily give you the mass or the scale. It depends on the size of your simulation. But still, it does seem, in my perspective, that the missing satellites problem without baryonic effects is still enforced in lambda CDM.
Okay. So it's better if you are baryonic effects, but it's still there.
That is my understanding of the current research, yeah.
I could ask a question. It's a bit general one. But I'm always confused about that stuff. So is there actually anything they do in this models beyond looking whether the usual general relativity is right? Because obviously it doesn't solve any of those initial problems with the cosmological constant that people usually.
I mean, it does solve the mismatch with the cosmological constant because the vacuum energy is predicted by lambda.
Yeah, but the vacuum energy for particles is predicted very much big. And the people who use FFR, I mean, in the beginning they introduced this function of the richest halo, but they don't have the cosmological constant is 0, so that problem isn't solved at all.
Yeah.
And the Gordon's problem isn't solved either because you just have some free parameters that you have to set at a certain point, which is exactly the same thing that cosmological constant.
Yeah, I mean, that's a very valid point, that there is the case that this doesn't necessarily play the 2 dragons that I introduced, but it does explore potential modifications. And whatever would slay the dragons would likely be a modification because the existing theory does not slay those dragons.
Actually, I'll ask one last question, which is, when you were showing the agreement between halo finders, you showed poor agreement in high mass. Where do high mass things?
Yeah, so let's go back to that plot, actually. So, yeah.
There are, some different numbers, fraction of halos which found these. And that could be that perhaps several of these high mass halos were merged into one very high mass halo by a particular finder. And other finders found 2 halos or 3 halos even. So depending on how a particular finder functions, the matching algorithm may actually match one of those little halos to a big halo, for example. And then you have 2 relatively big halos that aren't matched to any halo in that case. So that's one example.
So there's no way of defining 100% other than who finds the most.
So yeah, when we did the comparison, we actually, for some quantities, we used the complete halo finding catalog, and we only compared those halos which were found by all halo finders. So that kind of helps you have a more robust definition of a common halo.
Okay, I guess this point we'll thank Christine and move to executive session.
Thank you.